Cn. I'm assuming that Cn is real. We can do the complex case. It doesn't matter. It's okay to think of Cn as real. It doesn't matter. But let's let it be real. If it wasn't real, then we would want the complex conjugated. But we can choose it to be real, and then n plus 1. That's the exact same equation, except kets go to bras, operators go to their Hermitian conjugate, and numbers go to their complex conjugate, but I'm taking C to be equal to a real number. Okay, now, here's what we're going to do. We're going to put this equation next to it. We're going to take the inner product of this equation with this equation, with the bottom one with the top one. Let's write it out. N, A minus, A plus, N. That's what happens if you take the inner product of the left side here with the right side here. And that's going to equal Cn squared times the inner product of this vector with this vector. But what's the inner product of this with this? 1. 1. Every one of these vectors is normalized to 1, so it's just 1. So now we have a tool to figure out what Cn is. All right, all we have to do is juggle the A pluses and A minuses in a clever way. What do we want to do? I think I erased an equation over here. I should have written, yeah. Let's write down the guiding equation over here, or over here. N on the nth state is equal to little n on the nth state. Why is that true? What? Definition of being an eigenvector. Little n is the eigenvector of big N. Big N acts on the eigenstate with eigenvalue n to give little n. That's the definition of an eigenvector. Yes? Because I've used the rule. No, now I've assumed they're normalized. I'm assuming now that the n vectors are normalized. And having... I have put the ambiguity into the sequence. I may assume that they're normalized and then seek to... Got it? Right. Yeah. Okay, good. All right, so big N is nothing but A plus A minus. So let's put that here. A plus A minus that's almost what I have here. A plus, I don't have A plus A minus, I have A minus A plus. But what I know is what A plus A minus does. What can I do? What's that operation? Commute. Commute. And here is our commutator. The commutator is 1. So what that says is that this same thing is equal to n, A plus A minus, plus 1. That's the commutator term, n. Okay, now I'm in good shape, because I know what A plus A minus does when it acts on n. It just multiplies by little n. So all of this just gives me n plus 1 times the inner product of n with itself, which is what? 1. So there we have it. Cn squared is equal to n plus 1, and therefore Cn is the square root of n plus 1. We now know what the creation operator does in all of its glory. It increases the occupation number by 1, and it multiplies by the number square root of n plus 1. We can get rid of the rest of this. We don't need it anymore. Next, what about A minus on N? Well, you go through essentially the same little game. You can do it yourself. It doesn't take, it's not very hard. This time you don't even have to do any commutator. They'll wind up in the right order, and what you'll find out is that this is equal to the square root of n times n minus 1. In other words, it takes you down a level, but multiplies by the square root of n. Notice that this one, yeah, okay, that's what you find. Once you know this formula here, you don't have to worry about the fact of what happens when A minus hits the bottom level. When A minus hits the bottom level is n equals 0, you get 0. So this equation as it stands now encodes the fact that the lowering operator annihilates or kills or gives 0 when it acts on the ground state. That's just the square root of n. So this is more oscillator